Okay, so good evening, everyone. I cannot see anyone in this meeting right now. Maybe there is some issue with the link or the Teams link is not working. So I'm Shahzan Bhatt and I'm a direct PhD student at IIT Bombay. And in the week zero, we talked about the basic electrostatics problems and how to deal with them in the semiconductor devices and what applications are we considering in the semiconductor devices. So we solved some of the basic problems in the week zero. Now we are moving to week one, which is again the some of the basic problems, which include the some basic quantum mechanical problems, which are very important for the semiconductor devices. So now, if we talk about the brief course outline or the course layout, how the course will go as per the NPTEL website. So in the week zero, you might have covered the different aspects of the semiconductor, their applications, and their different semiconducting materials. So, and the different energy levels in the atoms, the energy band formation, and the band gap. So all of this comes because from the quantum mechanics. So all of the energy band formations in the atoms, in the molecules, in the solids comes from the quantum mechanics. So that's why this week zero will deal with some of the basic quantum mechanical problems like solving the Schrodinger equation, computing the momentum of the photons, how the photons interact with the material with certain band gap, how the band gap is formed, and what is the concept of the effective mass, what are the electrons and the holes inside the solid state devices. So you might have studied about an atom atomic picture, and if you solve the Schrodinger equation for that, you get discretized energy levels. Then you combine two atoms, and it makes a molecule. Then you see that those energy levels have behave differently when we solve the Schrodinger equation. And when you combine more of the atoms together, you get a let's say a periodic structure, and that is what you kind of transition from the single atom to the solids, and you again solve the Schrodinger equation, and what you get is the energy levels again, but with certain allowed energy levels and certain allowed energy levels and certain energy levels which are not allowed. So this all will be dealt basically in this week one, and you might have already covered that. But what this week one problems are all about is to make you understand what are the different problems, simplistic problems regarding the basic quantum mechanics, which will be taught in the week one. So let's directly dive into the problems and basically discuss each of the problems in detail. And I have directly taken the assignment sheet over here so that we don't have any problems in checking the answers, basically. And we will directly uh, deal with each of the problem in depth. So first of all, starting with this problem one, let's start with the problem one. And for a time being, you can ignore these answers which are written here. Don't just directly look at the answers because we are going to see what all how to arrive at this particular answer. Maybe there might be multiple ways of arriving at the single answer and doing a certain set of problems. So I request you not to just directly look at the answer and think that yes, this is going to be answer of this question. Some of the initial problems are very simpler. As you go towards the other problems which we will be solving, it will may become little bit of complicated, uh, and sometimes maybe the answer given may be incorrect, maybe because of some mistake. So okay, let's get started. First of all, let's say the question first, what the question first is saying. First of all, let's try to analyze the energy of a 500 nanometer photon. Is We have to compute the energy of a photon with lambda equals to 500 nanometers. It's a very simplistic question which can be computed by the energy can be basically computed by Planck's law. So E equals to h nu, where nu is the frequency of the photon. And you know that frequency can be written as C over lambda. So this is the overall energy of the photon. And it's the simple equation which we have studied in 10 plus 2. And how are we going to solve it is using the Planck's constant 6.626 in 10 to the power minus 34. You should remember the unit joule seconds into 3 into 10 to the power 8 meter per second. Let's use the units meter per second, and the lambda is given as 500 into 10 to the power minus 9 meters, which is the nanometer. So let's compute this thing here. Maybe we should open a calculator to compute this thing. If you have 6.626 into 3, you get 19.878 divided by 500 into 10 to the power minus 34 plus 8 plus 9. And when you divide this thing by 500, you're going to get 0.039756 into 10 to the power. This is minus 34 plus 17. So you get 0.039756 into 10 to the power minus 17 E. Now you have to measure it in the units of electron volts. So what you are going to do, this thing is in joules, you're going to divide it by electronic charge in order to compute this in electron volt, which is 1.6 into 10 to the power minus 19. And this will convert it into electron volts. Now, when you divide this thing by 1.6, this is going to give you 0.0248 force into 10 to the power. This will go up. This is 2. So this is approximately 2.48 electron volts. So this is the energy of a photon with a wavelength of 500 nanometers. So the answer of this question is 2.42. So what does this mean? This means that if you have a, let's say, a photon is basically a quantum mechanical picture, first of all. It is not directly what you might be thinking, that it's some kind of a electromagnetic wave. Yes, definitely it is. But when you go to a single particle picture, that is how you arrive at a photon picture. And this particular question is about a photon. Okay, so what is the difference between a photon and an electromagnetic wave? Then that you basically study in the higher classes, quantum mechanical picture of a photon. How does a photon arise from quantization of the electromagnetic field? So if you have, let's say, an electromagnetic field like this, you have the electric field, you have the magnetic field. Let's say this is the electric field. These are the curved ones. The underlined ones are the highlighted ones is the magnetic field. Let's say this is E field. Let's say this is H field. And they are mutually perpendicular to each other and perpendicular to the direction of the propagation, which is this direction. And they are perpendicular to each other. So when you do something called as in quantum mechanics, when you go higher, there is something called as quantization. You might have heard somewhere in the basic quantum course. And when you quantize this particular thing using something called a second quantization, which I don't want to even touch in this course, then you get a photon picture. And it's a very simplistic explanation what I'm telling you. And this particular question is basically about that. It's a photon which is having the wavelength of 500 nanometers, and its energy is basically 2.48 electron volts. It's in simplistic language, which we needed to compute, and we have computed that using simple Planck's law. And this particular thing is basically this gives you a quantized energy. The quantization came because of this particular thing, because it explained that the photons actually come in a packets. It's actually E equals to NH nu. So there are packets or quanta of photons being emitted. It doesn't matter what emits it, but these are emitted in packets. That's what this quanta refers to. So this was the first overview. This is the first question, and we have kind of solved this first question pretty easily. without going deeper into the explanation. It's a very simple question. So now question two, again, just omit this answer here for a moment. The question two says that the momentum of one electron volt photon is. Now, you see that what is momentum? It is the product of mass into velocity. You have been seeing this all the time from classical mechanics, classically. Okay, so the product of mass into velocity gives you the momentum of that object. And let's say if you have a photon, now it's a quantum mechanical entity, which I don't want to tell you about more about the photon. Let's consider it as a quantized particle which comes from an electromagnetic wave. Okay, you have a photon and it's having energy of 1 electron volt, and let's say it's moving, then because it's moving, it possesses velocity. But all of you might be knowing that the photon mass is equivalent to zero. Then how are you going to compute the momentum? How are you going to compute the momentum? It turns out that this basically is the rest mass of photon, which is equivalent to zero. Not the, I should say, if you check the relativistic mass of the photon, that might be different. But this is the rest mass of the photon. But nonetheless, we're not going to compute the momentum by invoking the mass of the photon. So what we are going to do is that we know from the the de Broglie relation tells us that the momentum is given by h over lambda. Okay, now we have the energy, we don't have the wavelength, so we can multiply c over c in the numerator and denominator, and this thing basically gives you the energy of photon, and you have energy divided by speed of light. So this is the momentum of the photon. Now it is very bizarre to see that despite there is no mass for a photon, rest mass basically, still it can possess momentum. Now the question is how. Again, in order to understand this, there is a very deeper explanation. But you know that if you have, let's say, if you have a laser, if you have a laser source coming from this side, and if you have a laser coming from this side, and if you have some very small particle, a very small particle, a quantum-sized particle, small, okay, if you have a small particle here, let's say there is small particle, then you can actually trap this particle with the help of a laser. These are lasers. And how does that happen is because this light source, which is a coherent light source, consider it as a light source, it's a laser, it has some pressure called as radiation pressure. And radiation pressure is basically it's if it's let's say it's denoted by let's say if it's denoted by uh, let's say if radiation pressure, let's say if it is P, then pressure is basically force per unit area. That means it is imparting some force. The electromagnetic wave is imparting some force onto this particle, and those forces are balancing and it's keeping this particle stationary. It's something called as optical trapping. And this is a very I should say a hot application nowadays, and a research area. And the simplest explanation, what I'm trying to make you understand, is that the photon possesses momentum despite not possessing the mass. It's because the photon possesses energy. And there is energy mass equivalence relation. If you have energy, you can convert mass into energy, you can convert energy into mass. And because of the energy of a photon, it possesses the momentum. Now, if you want me to explain the deeper truth behind it, there is a very, I should say, very uh, little bit of complicated explanation for how does a photon how photon has a momentum. Okay, so we won't go into that depth, but we can simply compute the momentum of a photon using this relation. So you can compute the momentum to be equivalent to energy is given, which is 1 electron volt, divided the speed of light is 3 into 10 to the power 8 meter per second. We need to convert the electron volt into the joules so that we don't mess up with the units. Earlier, we are given to compute it in electron volts. That's why we computed it in electron volts. Otherwise, this equation naturally gives the unit as joules. Okay, that's the SI units. And we will convert it into joules by multiplying with 1.6 into 10 to the power minus 19 electron volts, sorry, 1.6 into 10 to the power minus 19, and it'll be converted from electron volts to joules. So it is divided by the speed of light. And if you compute it, you are going to get, this is 1.6 divided by 3. So 3.53. So you're going to get 0.53 into 10 to the power minus 19. And there is 10 to the power minus 19 plus minus 8. So you get 0.53 into 10 to the power minus 27. Or it can be written as 5.3 into 10 to the power minus 28. And the units are kilogram meter per second, which is the in SI units. So the answer of this question will be 5.3 into 10 to the power minus 28. Okay, so let me just clarify the units. Maybe if we have converted it from 1 electron volts to joules, we have multiplied it with 1.6 into 10 to the power minus 19. So you can write it as 1 joule divided by the unit of velocity is meter per second. So you can write joule as joule is the energy. So it is unit will be similar to half of mv square. There will be meter per second in the denominator. So the unit of numerator here, it will be kilogram meter square per second square, and it will be meter per second. And there meter goes, kilogram meter per second will be the unit of this. So using simple dimensional analysis, you can compute the unit of momentum here, which is the momentum of the photon imparted on any object. So because of the energy possessed by the photon. Okay, so this was the unit checking and everything works fine. Now, uh, if I'm going too fast, then you can anytime just watch over the YouTube, and you can slow down the video basically. And I'm going a little bit of fast in these questions because they are very simple questions and they don't need a very deeper explanation because they are a simple 1 minute problem. Even though we are spending more than 1 minute on a particular problem due to the because I'm explaining it a little bit in a deeper way. So now moving on to this particular problem. Again, now you have a problem here that the you have to compute the ratio of momentum of two electron volt electron and the momentum of a photon of same energy. That means you have an electron, you have a photon. Let's say this is a photon. Let's say this is a photon, and this is an electron. First of all, the difference between the electron and a photon on a very basic level is that electron is actually a particle. We consider photon to be as particle also, but what happens is that the photon is basically it comes basically from a field quantization. You quantize the electromagnetic field, and from it arises the picture of a photon. But electron is definitely it is a particle which is present and is under the force of a nucleus and is present in the atoms. So the photon is produced because of something. When the electron and the hole annihilates in a semiconductor, it gives rise to a photon with certain energy. So this is basically comes from the excitation of certain modes in the electromagnetic wave, and you get a photon picture. So let me just simplify this particular problem and compute the momentum of both the electron and the photon. So if you have let's say, if you have electron, now you can simply compute its momentum. Let P denote the momentum, then you can compute the momentum of the electron to be, you know that the kinetic energy can be given by half of mv square, or you can write it in terms of a momentum as p square over 2m. So then the momentum of the electron can be written as under root of twice m e k, but this is basically given as two electron volts. So you can write the electron momentum to be equivalent to 2 into 9.1 and 10 to the power minus 31 kgs into 2 electron volts. Again, you need to convert everything to SI units, and you don't want to mess up with the units here. So it has to be converted into joules. So you need to multiply it with 1.6 in 10 to the power minus 19 joules. And now to simplify this particular problem, we need to compute it again. 2 into 9.1 into 2 into 1.6, that is 50 under root of 58.24 into, this is 10 to the power minus 50 simply. And if you want to compute this thing, under root of 58.24, so it will give you 7.63 into 10 to the power minus 25. So the electron momentum is 7.63 into 10 to the power minus 25. Again, the units will be kilogram meter per second. So the units are in SI units. Now, note that here we are using the mass of the electron because electron has a mass. It has a physical mass, a measurable mass. But the similar equation cannot be used in case of a photon because a photon, you know that the rest mass of the photon is zero, and we cannot exactly use this similar equation. And we have to use the previous equation, which is the momentum is equivalent to energy divided by the speed of light. And here we know the speed of the light because it's a universal constant if it's traveling in a vacuum. So we know that particular value. But since the question does not mention any of the material through which it's traveling, we are assuming it's a vacuum. So we are using this particular relation here, which we showed in the previous question, how we arrived at this particular relation. So we can compute the momentum of a photon by again putting the value 2 electron volt. 2 electron volt divided by 3 into 10 to the power 8 meter per second. Need to convert this unit into joules. So we write 1.6 into 10 to the power minus 19 joules divided by 3 into 10 to the power 8 meter per second. And when we do the multiplication, we get 3.2 divided by 3 into 10 to the power minus 27. So how much is this? This is 1.066 into 10 to the power minus 27 kilogram meter per second. This is the momentum of the photon. It's calculated as done in the previous example. And now what we need to compute is the ratio. So the ratio of momentum of electron. So the electron momentum, let me just change the color. The electron momentum divided by the photon momentum. Now we just take the ratio as 7.63 10 to the power minus 25 divided by 1.066 into 10 to the power minus 27. So what we are going to get 7.63 divided by 1.066. We are going to get 7.15 into 10 to the power 2. So this is the ratio of the momentum of the electron. So it's approximately 7.15 into 10 to the power 2. So this is the answer of this question. So note that here you see that there is the electron momentum is approximately 715 times the photon momentum. It's a very huge increase in the momentum. Why? Because just like I told you, because electron has some physical mass, even though it's the mass of the electron is of the order of 10 to the power minus 27, sorry, 10 to the power minus 31 kgs. But this certainly has a momentum which is 715 times that of the photon momentum. And clearly you can see that the momentum imparted by the photons onto any of the material is it's very low. That's why you need very large number of photons to impart certain momentum onto a particular material. If you say, let's say, if you increase the number of photons, if you increase the number of photons hitting any particular surface, you are going to increase the momentum imparted by those photons onto that particular surface, and appreciable momentum can be generated by those photons. So, but that's not the case with the electrons, because if you see using this relation, then you can directly see that the momentum imparted is much greater than the momentum imparted by the photons. So because electron has certain physical mass, that is what this problem is all about. Okay, so moving on to the next problem, we have it's a very now again it's something called as toy problem in quantum mechanics, where you have a potential well and there is a certain electron which is confined in that well, and you have certain solution which comes from the Schrodinger equation. So what we are going to discuss here is a potential well problem. Okay, so let me just zoom it out. Maybe we can use this space. Okay, so let's take the details from here. First of all, you are given a wave function which is c sine of kx for all 0 to L. This is a wave function. This is a wave function of electron. We are not told whether it's an electron or something. Let's say it's a wave function of a particle inside a potential well. So what is a potential well? First of all, what is this potential well? So if for example there is some positive charge here, and the electron is kind of moving through that positive charge, there will be electrostatic potential between these two charges. And because of that, when you map it, you get something like this. It's like a well where the electron is trapped in the potential of a nucleus, or of a nucleus or of a positive charge, and you get this well type of structure. Your basic electrostatics can give you this similar curve, where you will be seeing that there's a well type formed because of the electrostatic attraction, electrostatic interaction between these two charges. Now, a similar thing happens that we can artificially create such potential like this. It's not as sharp as this, but for the sake of understanding, we just show the potential like a well, like a square well. It's called a square potential well. And what happens is that usually the potential outside is zero, is the potential outside is infinite, and inside it's considered to be zero. And it's for the sake of simplification of the problem, which we will be maybe in upcoming courses we will be talking something about finite potential well. We call this potential well as infinite potential well. Why this is infinite? Because this particular well is infinitely deep from this particular from the top, and that's why the top is marked as the zero, and the lower you go, there is a kind of a negative potential created by the some charge here, which is the scenario is exactly like this. So it's under the influence of this positive charge. A similar kind of a situation arises here. Now, how do we make this kind of a potential well? Well, we do certain type of let's say fabrication steps. Let's say this is some one material one, this is material two, this is material three. When they are stacked over each other, let's say like this. Let's say this is material one, material two, material three. I don't want to discuss the materials for the simplification process, but if these materials are having different doping concentrations, they will give rise to different band gaps. And basically, this is the band gap of certain material. This is the band gap of other material, not this one. There will be this band gap. There will be this band gap. So you can get a well like this, where this particular thing is the band gap of one material. This particular thing is the band gap of other material, and this particular thing is the band gap of other material. So let me just show you more clearly what I mean to say, and how do we generate this potential well, and what is the implication of this potential well. You see that if we have a material and we stack the material over each other, and usually this particular layer where the well is formed, it's usually kept in the order of nanometers, few nanometers. The reason is because this should be of the order of electron wavelength in order for the quantization effects or the quantum mechanical effects to come into picture. Electron wavelength. So that is lambda e. So this particular width should be of the order of electron wavelength for the quantum effects to come into picture. Otherwise, if you just go on increasing this particular layer, it's not going to show the quantum effects, and there will be no quantization what we are going to discuss. So let's say you made certain materials. Let's say this is some width, this is certain width, and this is having certain width. And let's say this is material one, material two, material three. Then because of the nature of the energy levels, you get a potential well profile like this. Okay, where you see that this potential is infinite. That means this is a very deeper well outside, and this potential inside we consider zero. And this is for the simplification of the problem. And that is what this problem is about. It's about a potential well, and it's about an infinite one-dimensional potential well. So what happens is that we solve the Schrodinger equation in this region because the electron is considered to be kind of trapped in this region. Just like here, when the electron approaches a positive charge, the potential energy curve looks something like this, and you see the electron is here, and because of quantization effects, there will be a formation of the discretized energy levels. Similar thing happens here. You get a discretized energy levels like here. And how do you get these discretized energy levels? You solve something called a Schrodinger equation. You solve something called a Schrodinger equation, which is minus h bar square by 2m dou square psi over dou x square plus some v of x psi of x. This is the potential basically, which is equivalent to E of psi. This is something called as time independent Schrodinger equation. There is no time dependent part here. And what makes it really important is that you can solve this particular problem for various set of potentials. The only change here is this: you have to change this potential for a different set of problems. Maybe if here, let's say inside this particular region, the potential is zero, V of x is equivalent to zero throughout, and you need to solve only in this particular region. You need to solve the Schrodinger equation only in this region, not the outside, because outside the potential is infinite, and there is no probability of finding the particle outside because potential outside is infinite. It cannot escape this inner potential. Okay, for an infinite well case. Now, because the potential is zero here, so you get a very easy differential equation, which is given by minus h bar square by 2m dou square psi over dou x square. This will be zero is equivalent to E of psi. Okay. Now, what you need to do is that you need to solve this differential equation. You can solve this differential equation by just reformulating it like this: d square psi by dx square is equivalent to minus twice m over h bar square E psi. You can write it as d square psi over dx square plus twice m E divided by h bar square into psi. Psi of x is equivalent to zero. Now, it's a very simple differential equation, and you can pretty much easily solve it by considering that now what do you need? You need the boundary conditions. How many boundary conditions do you need? You need two, because the order of the differential equation is two. And what are the two boundary conditions? Let me just take this particular thing from here. Let me just copy this thing, and we will discuss this thing in a bit more like here. So this is problem number. This is problem 4. So this is question 4. Okay. So what we need to do is that we need boundary conditions. What are the boundary conditions? If you look at this potential well, we know that the potential outside is infinite and inside it's zero, and particle only exists inside the potential well. That means at these particular boundaries, the psi, which is which shows the wave function of the electron, and psi square gives the probability of the electron inside the well, probability of the electron. So we note that at these particular regions, psi should go to zero because the particle cannot exist here or here. There is no way particle can escape this. So if this is x equals to 0 and this is x equals to L, then this is the overall width of the well, which is equivalent to L. then the first boundary condition is that psi at x equals to 0 is equivalent to 0 and psi at x is equivalent to L is equivalent to 0. So this is the boundary condition. Okay, now what you need to do is that you need to solve this particular equation. How do you solve this simplistic differential equation? You know that this is the type of differential equation where you can write the operator d square psi plus some k square psi is equivalent to 0, where this k square is twice me over h bar square, and you can write k to be equivalent to under root of twice me divided by h bar square. Okay, now you solve this particular thing like this: d square plus k square psi is equivalent to 0. You solve this thing, the differential equation course, you definitely know that you get a solution. You get a solution like you can get solution like psi of x is equivalent to uh, some constant c sine of kx. This is the solution of this, and you know it's a basic mathematical differential equation. You know how to arrive from this particular thing to this particular thing. You basically need to solve this, and you get a you know that now the what this particular k is. This is this thing. This is called as wave vector. Okay, let's not go into this thing but right now. But let's say this k is something defined as this, which is dependent on the energy of the electron, and it simply came from the Schrodinger equation. Now this particular thing is given to you. It's given to you in the question that a wave function with psi x equals to c sine of kx is given to you, and you need to find this particular constant here, which is in front of it, the coefficient. How are you going to find it? Now, remember that if this is a potential well, then the probability, and if you draw this particular thing here, there is an energy n equals to 1, and this looks something like this. This is n equals to 1. Okay. And when you again solve this particular thing, you note that this particular sign of kx, when you use the boundary conditions, you arrive at a condition where k is only an integer multiple of n pi by a. Okay, and how do you compute this, or how do you arrive at this particular thing where you can define this particular k to be equivalent to n pi by a? Now what we are dealing here with is we need to simply solve for this particular c here. And how are we going to do it? We know that a particle, the probability of a particle is equivalent to 1 inside. That means the particle has to be somewhere inside the well. Particle has to be somewhere inside the well, because it cannot go outside. So probability should be equivalent to 1 inside, at least where we are going to trying to compute it. That means the particle has to be somewhere. Okay, how is this probability written? It is written as minus infinity to plus infinity psi star psi dx is equivalent to 1. And this basically comes from Born rule. It's a Born approximation. So it's something called as Born probability rule, which says that the probability is basically given by mod psi square dx, and this is equivalent to 1. That means the probability of finding a particle is 1. That means that there is the probability that particle will be somewhere. Okay, that's why we write this psi square as a psi star psi, because the wave function can be a complex quantity. So we write it as psi star psi, and the complex conjugate psi into dx is equivalent to 1. Now you are given this psi, you are given it as c, the psi of x is given as c sine of kx, and what we are going to do here is that, note that don't confuse yourself with this particular thing here. One thing I want to just emphasize here is that this particular k here is n pi over a. and you don't confuse here with this particular k. Let me write it as k, capital small k, which I have named this particular variable. Maybe you might get confused. In this particular case, capital K, which is basically the wave vector. This is the wave vector. Okay. So what happens is that now you solve this particular thing, and you know the limits you have to change because you are confined to a well. You are confined to a well which has limits of 0 to L. Okay. So now you using that, you can use 0 to L, C sine of kx into c sine of kx. It's not a complex quantity, so both of the psi star or psi will be same. Dx is equal to 1. You can write it as c square sine square kx. Dx is equal to 1, 0 to L. Now, how do you solve this particular problem? This is an integral of sine square theta. You have to convert first into a, you have to omit this square. You cannot directly solve this integral. So you can write it as integral of 1 minus cos 2 theta, which is kx, divided by 2 into dx. And this particular thing is 1. And now c square is outside. Now you have to integrate. The integral of, let's take 2 outside. The integral of 1 with respect to x is x minus integral of cos 2kx is sine 2kx divided by 2k. The limits are from 0 to L. That this should be equivalent to 1. Now you write c square by 2, applying the limits. First applying the upper limit. When you apply upper limit to x, it gets equivalent to L minus sine of 2kl divided by 2k. Now minus 0. When you apply 0 to x, you get 0. Minus sine of 0 is 0. So this is 0 is equivalent to 1. So you get c square by 2. You get L minus. Now, what you are going to get is that k equals to n pi over a. This is going to be used. It's n pi over L here because we are denoting the width of the potential well as L. And here n is equal to 1 because sine of kx is basically the for k equals to n pi by L. If n is equal to 1, you get k equals to pi by L. So that is the first energy level in the potential well, which is the n equals to 1 energy level, where you get this particular solution. If you draw this is basically psi of x in n equals to 1. And now if you use that here, you get sine of 2 n is 1 pi L divided by L divided by 2k. And this L and L goes, sine 2 pi is 0. So you get c square by 2L is equal to 1. You get c square is 2 over L, or you get c to be equivalent to under root of 2 divided by L, which is something called as normalization coefficient. Normalization coefficient. And it's necessary, this coefficient is necessary for overall probability to be equivalent to 1. That means it only if this is normalization coefficient is used before the wave function as a coefficient, then only this psi star psi dx can be equivalent to 1. You cannot say that if you have a wave function psi of x equals to sine of kx only, and you cannot say that the overall probability or psi star psi equals to 1. You won't get the correct result. That's why this particular normalization coefficient is important. It ensures that overall probability is 1. Overall probability is 1 because you know that the particle has to be somewhere. So it cannot be like the overall probability will be greater than 1 or overall probability will be equivalent to 0. These two cases cannot happen because you know the if overall probability is greater than 1, probability cannot be greater than 1 first of all. And if probability is equivalent to 0, then that means the particle is not there. Particle not there. And that is not possible. The particle has to be inside this infinite potential well. It cannot escape through any means. Later on, you will see if you have if this is infinite potential well. Later on, you will see if you have a finite potential well, where the infinite here is, let's say, u1, and infinite outside is let's say, u1 again. You will see that there is a finite probability that the particle will escape through this potential well, something called as tunneling, which we will be talking about in one of the questions, maybe uh, in this assignment problem. But this is the importance of this normalization coefficient, which is important for maintaining the overall probability to be equivalent to 1. I can still see that nobody has joined this meeting, so maybe there is some issue with the link. But let me check the mail if somebody might have mailed me if you guys are not able to join. Okay, anyways, so this was question number 4. I think we discussed it too deeply. Uh, okay. So if you have a confusion of how we got to this, you can basically use the boundary conditions, and you can write that psi at x equals to 0 is equivalent to 0. That means C sine of kx is equivalent to 0. The C cannot be 0, because if this is 0, then overall wave function is 0. So this thing has to be 0. Sine kx equals to 0. And you can write that means kx is equivalent to integer multiples of pi, where n is equivalent to 1, 2, 3 integer, positive integers. And from this you get k is equivalent to n pi over x. And the similar thing is basically at x equals to L. So if x equals to L, this thing is L, this thing is L, this thing is L, and this thing is L. So you get k equals to integer multiples of n pi, integer multiples of pi over L. So that's how you get this particular thing. I didn't want to kind of leave it like this. Maybe some of you might be having the confusion how you arrived at this. Basically, you use the boundary conditions. Okay. And as I said, there are two boundary conditions. The two boundary conditions, one at one boundary and another at the other boundaries. So that simplifies the problem, and you get the solution of this particular problem to be of this form. And you arrive from this thing to this thing, and then you arrived at this thing, and you use the boundary condition to obtain the wave vector, and you get the solution. You use the Born rule to compute the probability and to consider the overall probability to be equivalent to 1, and you get this something called as normalization coefficient, which is important to maintain the overall something called as maintaining the norm of the this probability density function. So I don't want to use the jargons here, but it's for maintaining the overall probability to be equivalent to 1. So this is all about question 4. Let's move on to the other questions. We have 1 hour remaining. Now we have the question number 5. Let's take the details from the question 5, and we will solve it maybe here, because we have enough space. Consider an electron with an energy of 1 electron volt impinging on a potential barrier with V naught equals to 5 electron volt. First of all, we need to think about this problem, what this problem is saying. It's an electron moving with certain energy equals to 1 electron volt, and it is impinging means hitting a barrier, potential barrier. There's a barrier like this where the electron is hitting, and this barrier is V naught equals to 5 electron volt. And the width of this potential barrier is 0.5 nanometers. Now we need to compute the tunneling probability. What is this tunneling probability here? This is a very important word, and this is a very crucial concept in quantum mechanics. The tunneling probability is approximately given by, we need to compute how much is the probability that an electron will go through this barrier to the other side. Now let's discuss this particular problem in detail. Let me copy this thing. This is question 5. This is question 5. So let me paste it here, and let's start. This is question number 5. So all of the details we are given here. Now, first of all, you need to understand it's a similar problem to what we earlier saw. We saw that there was an infinite well where the potential was infinite and the electron was trapped here. And this type of well was created, let's say, if an electron was under the attraction of a nucleus, and then it forms like a well type of a potential where the energies are discretized. It's formed by that kind of a scenario, or it's formed by if you stack certain layers of materials over one another, maintaining the thing that this particular confinement layer is of the order of electron wavelength. Okay, then you can see the confinement effects. Confinement effects basically means the discretization of the energy levels. Then you can use the Schrodinger equation in order to compute the energy levels. Now, this particular scenario here is a little bit different. Let me drop this particular thing here. This particular scenario is different. Why? Because first of all, let me drop this, and let's say the electron energy given is 1 electron volt. It is different because it's not, first of all, infinite potential well. It's something called as finite potential well problem. Finite potential well problem. And just like in classical mechanics, if you have a ball and if you threw it at a wall, because you know that if there is something at the top of the wall, then it's having the gravitational potential energy. Okay, the gravitational potential energy, let's represent that as UG, is given by the H rho G. No, not it's mgh, the mass times the gravitational, the acceleration times the height of this well. So this is the gravitational potential energy, and but this is the barrier for a wall. This is a wall here, and if this ball has to cross this wall, this is a wall. What this ball has to do, it has to go over the wall and appear on the other side and go on the other side. Then it can come over this side. Okay, that's the only scenario classically it can do. Now, somebody will argue that a wall can just hit this wall and break this wall and get on the other side. But no, the energy is not that sufficient to break this wall. You can classically break this wall, but energy is not sufficient for a ball to break this wall. It's let's say a rubber ball. It cannot break a wall. The wall is very thick and it uses bricks of very large thickness. So this is a scenario classically, and there is only one option, that it has to go over the wall in order to appear on the other side. Now, it appears that things in quantum mechanics behave weirdly. Why? Because if you have a, let's say, if you have a same, let's say, if you have a same scenario in quantum mechanics, you have the same scenario. What scenario? If you have a wall, a quantum wall, which is the potential barrier, let's say this is a quantum wall, a quantum wall. And if you have a ball, let's say this is a quantum ball, which is a quantum mechanical object. Let's consider this as a ball. Because of the wave nature of this ball associated with it, it is a wave. So when it hits this potential, when it hits this wall, when it hits this quantum wall, the wave starts to leak inside the wall, and somehow it appears on the other side. It is as if the ball has gone through the wall, appeared on the other side. That is what has happened exactly. And that is what happens quantum mechanically because of the wave nature of objects. And we see this often happening with the light, basically. The light has a similar behavior also, but I don't want to go into that depth here. But what is happening is that because of quantum nature, and we will see how we arrive at these solutions, how we show that this is a wave, this is a decaying wave, this is another wave. Basically, we solve the Schrodinger equation, but quantum mechanically, this is happening. So a wave, a ball is treated as a wave, and it goes inside it tunnels inside the wall and appears on the other side. Now, how do we get to this problem? And what is the scenario? So you treat electron as a wave here, and the wave is something plane wave. It hits this wall. It tunnels inside this wall and appears on the other side. let's call this region 1, region 2, region 3. Okay, now you might have studied in your lectures, you solve the Schrodinger equation for region 1, region 2, region 3. Okay, for region 1, it's quite easy because there is the potential outside this you consider to be 0, the potential outside is 0, the potential inside there is 5 electron volts. So when you solve the Schrodinger equation, you get psi of 1, the wave function 1 to be equivalent to a e to the power minus iota, let's say kappa x, where this is a kind of a plane wave. You know, this is a plane wave solution. It's a plane wave traveling in this direction, traveling in this direction. Okay, note that here there is no time dependent part of it. It's just a spatially dependent thing. It's just a spatial dependence. We are omitting the time dependence right now. This comes because of solving the time independent Schrodinger equation. Okay. It's quite easy. Just like we solve the Schrodinger equation, we have to put the potential to be equal to 0. You get a plane wave-like solution. The particle is it's like a free particle outside the barrier. Okay. Now inside the barrier, you get a solution psi 2, which is a little bit of weird. You get, let's say, some coefficient b e to the power minus kappa. This, let's say, this is kappa 1, this is kappa 2x. This is the decaying part. This is not e to the power I. This is e to the power kappa only. This is a decaying wave. Decaying wave. And outside you get again psi 3 to be equivalent to let's say c e to the power I minus I kappa 3x, where this is again a plane wave. This is a decaying wave, exponentially decaying wave, and this is again a plane wave. So you have these three wave functions in region 1, in region 2, and in region 3. Okay, now this is quite easy to show that when you, let's say you write for region 1 and region 2, it's quite easy to write the Schrodinger equation. Basically, the potential is 0. But for the region 2, you can write the Schrodinger equation as d square psi over dx square plus twice m over h bar square u minus e psi of x to be equivalent to 0. Now you use this particular thing and you call this kappa. And this kappa is equivalent to, let's say, you call this kappa square, and you get kappa to be equivalent to under root of twice m u minus e divided by h bar square. Okay, this is divided by h bar. If you put the h bar in the root, then it's h bar square. So this is basically the k value which you get in the middle region. Note that it takes into account this potential of the barrier also. And this is kappa, this is basically kappa, let's say kappa 2. For this region, you will get kappa 3 to be equivalent to under root of twice m e uh, divided by h bar. And for this region, you will get kappa to be equivalent to kappa 1 equivalent to under root of twice m e divided by h bar. Okay, just comes from solving the differential equation, nothing else. Now, what you need to do, you need to find the tunneling probability. At the end, you need to find the probability. Let's say you have this barrier, and you know from the wave picture, if a wave is coming, it hits this, some part of the wave gets reflected, some part of it gets transmitted. You call this, let's say, incident wave. You call this reflected wave, and you call this transmitted wave. It's the same picture here. Now you find the transmission coefficient. Let's say you call this as transmission coefficient. You call this as reflection coefficient, and you compute these, and you see how much part of the wave gets transmitted, how much part gets reflected. That's as simple as that. Doing these things how we do in wave mechanics, simple wave mechanics. In any of the wave, whether it's a electromagnetic wave, acoustic wave, or any type of a wave you deal with. Now, what you do is that because you know the wave function here, You know the wave function. You take this wave function to its equivalent to b e to the power minus kappa 2x. Let's, for a time moment, ignore this b here. We can compute it using the boundary conditions. Let's use the approximate formula, because in the question you are told to use the approximate formula for the computing the tunneling probability. This right now is not a probability. This is the wave function in the region 2. Now, what we do is that we convert it into probability. How? The probability of transmission of this electronic wave will be proportional to psi square, psi 2 square. So that means it will be approximately equivalent to e to the power minus 2 kappa 2 x. And at x is equivalent to L, you get e to the power minus 2 kappa 2 L, which is the, let's say you call it T, which is the tunneling probability, is approximately given by e to the power minus 2 kappa 2 L. Now you have everything. You have L equals to zero point 0.5 nanometers. That means this particular thing is zero point 0.5 nanometers, which is a very small distance. That means it's almost, how much is 1 nanometer is 10 angstrom. Sorry, it's 1 nanometer is 10 angstrom. That means 0 0.5 nanometers is 5 angstrom. It's almost of the order of lattice constant, which is the space from the center of the two atoms to the other, which is this lattice constant. Okay, it's a very smaller distance and it's appreciable for tunneling to happen. You will see that tunneling probability, basically what happens to tunneling probability if you go on increasing L, tunneling probability will reduce. There will be less chance for the electron to leak out on the other side. And for the electron to leak out on the other side, first of all, there should be an electronic state present here. Then only it can leak out. That means if electron is leaking like this, exponentially decaying and appearing, there should be an electronic state here where electron can reside. Okay, now you see that the weird part here again is that the amplitude of what I'm showing is that amplitude of the electronic wave, probability wave, is higher here and lower here. That just comes from again solving the Schrodinger equation, and you will notice that there is a lesser amplitude of this probability wave when you go on the other side of the barrier. Now, what we need to solve is we need to compute this tunneling probability. This tunneling probability is approximately given as e to the power minus 2 kappa 2 L. You compute kappa 2 first, which is under root of twice m u minus e divided by h bar. How much will it be? It will be 2 into 9.1 into 10 to the power minus 31 into, this is 5 minus 1 electron volt into 1.6 into 10 to the power minus 19. This thing is coming because we need to convert from electron volt to joules. Okay, so divided by this is h bar. Okay, you need to take care of this h bar, as h bar is basically h over 2 pi, Planck's constant by 2 pi, something called as reduced Planck's constant, 6.626 into 10 to the power minus 34 joule second. 2 pi will go up into 2 into pi. Let's multiply all of this thing together and see what we will get. Let's see, this will be under root. Let's see, 2 into 9.1 into 4 into 1.6. So this is 116.48 into 10 to the power minus 31 minus 19 is minus 50, divided by 6.626 into 10 to the power minus 34 into 2 into 3.1415. So when you square root this thing, you get 10.79 into 10 to the power minus 25. We will take minus 34 up. This will become plus 34 divided by 6.626 into 2 into 3.1415. Now multiplying throughout by 2 and 3.1415, dividing by 6.626, you get 10.23 into 10 to the power minus 9. Oh, okay. It is minus is plus. So K, you get 10.23 into 10 to the power 9. And what will be the units of K? Let's check. This is kilogram for mass. This is joules, and in the bottom there is joule second. Now you can write joules as kilogram meter square per second square divided by joule, again kilogram meter square per second square into second. You will get kilogram is kilogram square. So you will get from the root kilogram meter second divided by kilogram meter square second square into second. Second goes, kilogram goes, meter goes. You are left with 1 over meter second square. So this is the unit of this particular thing, second square per meter. I think we messed up somewhere in the units, maybe. Okay, let's cross check it again. We will cross check it, and let's not right now worry about the units. We'll come back to the units again. Maybe we messed up with some SI unit, but okay, we got the K. This is kappa 2, sorry, this is kappa 2. Now you can compute the tunneling probability to be approximately equal to e to the power minus 2 kappa 2L. This is e to the power minus 2 into 10.23 into 10.23 into 10 to the power 9 into 0.5 into 10 to the power minus 9 meters, which is the nanometer. So this and this will go, and this and this will go, and you're all left with e to the power minus 10.223. So if we compute this e to the power minus 10.23, e to the power, you get 1 over 27830. Okay, uh, so basically you can write it as 1 over e to the power 10.23. You get 1 over 27830.93, and you can divide 2738830.93. You get 0.000033593. This is the tunneling probability, or approximately you can write the tunneling probability as 3.5 into it's 1, 2, 3, 4, 5 into 10 to the power minus 5. It has no units because it is a probability. So the answer for this is 3.5 into 10 to the power minus 5. 10 to the power minus 5 is the important thing, which is the order. What is the answer of this question? Okay, it is 9.2 in 10 to the power minus 5. Okay, so 10 to the power minus 5 is the important thing, which is the order of this probability. Maybe there's a mistake of this particular factor here, but the important thing is that you got the order of the probability same to as that in this particular answer. So I don't know, maybe there might be a mistake in this particular question, or we might have done a mistake in the units, but this is the actual this is the actual scenario or actual logical explanation of solving this such kind of a question. Now you will be given anything. An instructor can vary any of the things, maybe a potential, maybe the energy, and you have to compute the tunneling probabilities in these particular things. Okay. So let's quickly move on to other questions. What we are left with. It's a simple one here. So Schrodinger wave equation, you need to identify among this. We have used the Schrodinger wave equation multiple times. So it is this particular thing here, which is minus h bar square divided by 2m. So Schrodinger equation basically is minus h bar square divided by 2m d square psi divided by dx square plus v of x psi of x. This is in 1D, which is equivalent to e of psi of x. So now which of the following is matching this? Okay, so you write minus h bar square divided by 2m. So this particular thing is the answer of this question. So it's basically, if you just take, you can write it as h bar square by 2m d square by dx square plus v of x psi of x to be equivalent to e psi of x. And this particular thing is basically called as Hamiltonian. It is the total energy of the system, which composed of the kinetic energy part and the potential energy part. As simple as that. You don't need to think about. Now you will ask how this kinetic energy thing comes. Now for that you need to go into the I should say the foundations of the quantum mechanics, how this particular term comes up. And for that, you need to consider the operator of the spatial operator, the x operator, the momentum operator, then the energy operator. So basically, this is the energy operator, minus h bar square by 2m, rho square over rho x square. So when you quantize the physical variables, physical observables, physical observables are something you measure in an experiment, and they are the x, momentum, and the energy. Position, momentum, and the energy. That is what you measure experimentally. That's why they are called as physical observables. Physical observables. It's a very bad color to highlight. Okay, let's remove it. Now, when you do something called as first quantization, you quantize these observables. You get x as an operator, momentum as an operator, and energy as an operator. Okay, this is called as first quantization in quantum mechanics. Now, there is another thing called as second quantization. Second quantization, you quantize the fields and you get those photons, bosons, and other things. If you quantize the fields, let's say the electromagnetic field, the acoustic field, the gravitational field. You quantize this thing, you get a photon. You quantize this thing using second quantization, you get a phonon. You quantize this thing, you get a graviton. These are the individual quasi-particles, or the particles, I should say, of these particular fields, which you do by using something called as second quantization. But you don't need to think about it. But this is just an overview how the fields and physical observables get converted into their respective operators. And this is how the Schrodinger equation basically comes into picture. That's all about this question. And I think this is enough for this question. Now, for the question number 7, again, you are asked to choose the Heisenberg's uncertainty principle, which you all know that it is the uncertainty in position and momentum should be greater or equivalent to the reduced Planck's constant divided by 2. And you can simply understand this by Fourier transform even. If you know the Fourier transform, that there is uncertainty between the frequency and the time which is greater than 1 by 2. And how can you understand this particular thing? Let's say you have something like let's say you have something like a sine wave, and you compute its Fourier transform, you get something like this particular thing. Now, why do you get particular thing? Why do you get a band? Why don't you get an impulse as this? Because this particular sign in time domain, it is this is limited from 0 to, let's say, infinity. Ideally, the sine wave should be from minus infinity to plus infinity. Then only you can get a Fourier transform of impulse function, or a single impulse function with a single frequency omega naught. But if it's not from minus infinity to plus infinity, if it's like this, then you will get a band of frequencies. Because using the Fourier series, you have to basically add infinite sine components to get this particular thing, where the sine components here and the sine components here should cancel, because it's a time limited signal. You get a frequency domain signal like this. And that basically is one of the simplest explanations of why the Heisenberg's uncertainty principle is there, because there is a frequency time uncertainty. And because of frequency time uncertainty, you can write delta omega dot delta t greater than 1 by 2. You can write this as, in terms of energy, you can write this as delta E delta t greater or equal to h bar by 2, because you can write delta omega as delta E by h bar. Simply, that is the simplest kind of understanding of Heisenberg's uncertainty principle. Now, there are other variants of Heisenberg's uncertainty principle, like the position and the momentum, the energy and the time, the frequency and the time. These are other these are Heisenberg's uncertainty principle in other considering other physical observables and their uncertainties. And how this 1 by 2, or how this 1 by 2 factor comes, you need to again go into a foundations of the quantum mechanics, when you basically compute where you basically compute something called as the uh, something called as, let's say, when you do the quantum mechanics, you study about commutators and you compute about the commutation operation of these particular thing, and you see that the momentum and the position, they do not commute. That means they don't have a simultaneous eigen functions. Or in other words, if you apply momentum, if you apply a position operator over some wave function, if you apply a momentum operator over some wave function, followed by the position operator, you will get a different output. And if you apply position operator first and momentum operator second, you will get different output. A simple way of understanding this. But the commutation relation has a deeper meaning in quantum mechanics, which is regarding the not having the simultaneous eigenfunctions. But you don't need to think about that again. You can just relate using the simple Fourier transform, Fourier spectrum, from the mathematics. You can relate it with the Heisenberg's uncertainty principle. So the answer of this question is delta x delta p is greater or equal to h bar by 2 pi, h bar by 2, sorry. So don't get confused with this thing, because this is not reduced Planck's constant. This is h by 2. It is h bar by 2 on the right hand side. So h bar is h by 2, which is the reduced Planck's constant. Okay. All right. So moving on to the question 8. Now the question 8 says that an electron is confined in 1D potential box. Again, we are considering infinite potential well, where the electron is in n equals to 1 level. It has the wave function looks something like this, and energy is given by h bar square k squared divided by 2m. It again comes from the same fact, because we have written the, if you know that we wrote the small k as under root of twice me divided by h bar, and when you compute the e from it, you get h bar square k square divided by 2m. All right. So what we are supposed to do is that there are two energy levels now. There is energy at n equals to 3, and there is certain gap between n equals 1 and n equals to 3. Okay, let's call this E3, let's call this E1. Let's compute first E1, then we can compute E3. What we need to find is that we need to find the approximate energy in milli-electron volts of the emitted particle when it makes transition from second excited state to the ground state. So notice that here this n equals to 3 is called the second excited state. This is called as ground state. Okay, there might be some other level n equals 2, which is called as the first excited state, because if the particle is here in the ground state, it will excite here to the first excited state. Then it can go again excite here to the second excited state. That is how the terminology comes. Now let's remove this n equals to 2, because it's not talking about n equals to 2. Now what happens is that if a particle is here, it can make transition to n equals to 1, and it can emit any other particle, let's say a photon. And that photon will be having same energy as E2 minus E1. Okay, the energy difference between these two energy levels. Now he's not talking about photon, he's talking about any other particle, because it can emit a photon, it can emit a phonon even. Let's say that the emitted particle, let's say that the emitted particle is, let's say it emitted a particle, not a photon or a phonon. But we know, because of the conservation of energy, that particle should have the energy equivalent to energy difference between the two energy levels. It is E3 minus E1. Now we need to compute them separately, and we are done with the question. Okay, let's compute E1 first. E1 is h bar square k square divided by 2m. This k, we know that it is n pi over L, where L is this particular thing, and it's given as 20 nanometers, the width of the potential L. And this is n equals to 1. This is for n equals to 1, so it will be pi over L. Okay. And now we need to find E1. We can write E1 to be equivalent to, let's write h bar as h by 2. It will be h square pi square divided by 4 pi square, because we have written h bar as h by 2 pi, and this was h bar square. So this will be 4 pi square twice m. This will be pi L square. So you can write it as h square pi square 8m pi square L square, pi goes. You can write it as h square divided by 8m L square. This is E1. And E2 is basically again, this is n square pi square h square divided by 8m L square. N is 3, so you get 9 pi square h square. Actually, the pi cancels out, so you are not left with the pi. Let's remove this pi. You get 9 h square divided by 8 m L square. All right, so now this is E3, sorry, where n is equivalent to 3. Now you will compute delta E, which is E3 minus E1. You get 9 h square by 8 ml square minus h square divided by 8 ml square. You can take h square by 8 ml square common. This is 9 minus 1. This is 8 h square by 8 ml square. 8 and add O's, you are left with h square divided by 8 ml square. Now the only thing left is that to put the values of h and m. You use h to be equivalent to uh, you use h equals to 6.626 into 10 to the power minus 34 joules second, and m to be equivalent to 9.1 into 10 to the power minus 31 kilograms, and L is given as 20 nanometers. That means 20 into 10 to the power minus 9 meters. But remember to take the square of this. When you use all of these values, you will see that you will get 7.5 as the difference between the energy. Okay. But note that here you will get this value in joules. You need to convert it into electron volts. And whatever the value you will get in milli electron volts. That's the fundamental thing of it. Maybe you can do the computation here, but it is going to take a lot more time, and we are left with, I guess, four questions. But it's a very simple. It's a simple computation after it. You are going to get 7.5. But just thing is that don't get confused, because this will give you the value in joules. You need to convert it into electron volts, and you will get the value in milli electron volts, which is approximately 7.5 milli electron volt. So the emitted particle, this is the energy of the emitted particle. Emitted particle will have this energy of 7.5 milli electron volts. All right, let me draw a line here so that we can discuss other questions. Okay, so question number 9 says that silicon and germanium are, first of all, what are silicon and germanium? What is the direct band gap and what's an indirect band gap? When you, let's say, have atoms, these atoms make something like these potential wells, what you saw earlier in a solid. This is in solid. You have series of atoms. And when you draw this in a very sophisticated fashion, it looks something like this. These are again the same things, where these are the atoms here, and these are the potential wells, where now the electron energies are discretized. Okay, and now electron forms a band of energy somewhere, and it forms an energy level somewhere. But these inside energy levels are the deeper levels, something called as inner s orbitals, which are inner orbitals, and these electrons don't participate in any of the electronic conduction process. Usually there are the electrons which are present here, because you have a band of energy levels here. So the electron acts like a nearly free electron here. Okay, so this is something called as nearly free electron. And you get this picture by again solving the Schrodinger equation for these potential wells and using something called as block condition, where let's say a wave function at this particular position is e to the power minus I times ik a times the wave function at x plus a position. Basically, if you have wells, and this is, let's say, 0 to a, and this is b, then the wave function in this particular region and particular region are similar, except that there is certain phase associated with that, which is given by this particular factor. Let's not go deeper into that, because it's maybe the professor has talked about it. But what we have to discuss here is that there arises a picture of something called as direct and indirect band gap. When you see this picture in energy momentum space, okay, you get something called as band diagram. band diagram denotes the allowed energy levels of electron. And for let's say silicon, you get something like this, where this is the conduction band minima, and this is the valence band maxima. And for the germanium, again, you get a similar picture. Let's say this is silicon and germanium, you get a similar picture. And this is basically K in this direction, and this is basically energy in this direction. And what you see is that these two minima and the maxima are not located at same K value. Here the K value is different, here the K value is different. Let's say here this is K equals to K1, here the K value is K equals to K2. When this particular thing arises, you get something called as indirect band gap semiconductor. Indirect band gap semiconductor. And this particular gap is basically the band gap. All right. Okay. The gap between this thing level and this level. And why is it indirect? What consequences does it has is, if you just consider this band again, this is conduction band, this is valence band. If an electron has to go from this particular state to this particular state, it cannot directly go. Okay, it has to first change the momentum in K space. It has to change its K value and reach somewhere here, then it can transition from this particular level to this particular level. And while going from this particular state to here, maybe some state is present here, and then it drops to the valence band. It emits other kind of particles, maybe phonons, that heats up the system, lattice, that heats up the lattice. And that is why the silicon is not an efficient emitter of a light, because you know that if an electron goes from this to this level, like this, it will emit light. Okay, it will emit electromagnetic wave. And why does it happen? Yeah, that is having a different reason that goes into the quantum mechanical aspects. But for the electron to go from this to this particular region, it has to go from this to this state. Then it can go transition from this upper state to lower state. That means it has to change its K value. And while doing it, it emits something called as phonons, and it heats up the lattice, and it decreases the efficiency of the silicon used as a let's say as an LED or any kind of a light emitting source. This is the I should say the common problem with these indirect band gap semiconductors. That's why we use something called as direct band gap semiconductors, where the gap is direct, where the transition takes place directly. Electron goes from this place to this place directly, and it emits a photon of this energy. There's little or no phonons involved that can produce the lattice heating and other heating effects. Okay, so the answer of this question is it's a direct band gap. Sorry, it's an indirect band gap semiconductor. Okay, now lattice type of silicon is it's a very theoretical question, and you can understand pretty well that the lattice type of silicon is a diamond type. There are basically different types of lattice. Lattice is that how the arrangement of atoms is present inside the inside this particular material. If you let's say if you consider the body center, then there is a atom present in the body center, and there are atoms present in the on the corners of this particular thing. Similarly, if you have, let's say, some other type of a structure where there are atoms present on these corners of the cube, and then there are atoms present inside like this, present inside like a maybe a diamond or like a rhombus. So you can easily see some websites where you can basically see different structures of different structures of different materials. Certain websites related to like material science that can give you a notion or a three-dimensional representation of lattice types, and that means how these atoms are arranged, atom arrangement. Okay, let's move to the other question quickly. Which of the following is correct in terms of the conductivity? So conductivity is the how better electrons can flow inside certain materials. How better electrons can flow inside material. Okay, so you know that for a metal, if you draw the band diagram, remember that this particular thing is called as band diagram, where you represent energy in y-axis and this is a x-axis or the spatial coordinate. This particular thing is called as band. This is basically called as band structure, not a band diagram. This is called as band structure. Pardon me, but this is a band structure where you define energy in this axis and this is a wave vector in the x-axis. So this is basically the band structure. This is a band structure. That's a difference between the band structure and a band diagram. Most of the people are confused with it. But this is the band structure. This is the band diagram where you draw E versus X. And if you consider the metal, for example, then the Fermi level almost lies in the conduction band. It is in the conduction band, and there is the electrons present near this conduction band are mostly they mostly take part in conduction process, and there is no energy gap, and the conduction is maximum. Okay, so the conductivity basically is related to the number of electrons, the number of free electrons. It's related to the mobility, there's a particular relation for the conductivity. Okay, that means sigma is n e mu. This is the conductivity, which is the number of electrons, electronic charge, and the mobility of the electrons, how freely electrons can move. Okay, so in metals, they can they can move freely without any kind of without any scattering, without, I should say, facing any kind of most of the scattering processes are not present in the metals, and there are many number of electrons. Scattering processes are definitely present in semiconductors as well as metals, but because of more number of electrons and the free electrons in the metals, these are the more number of free electrons in the metals. It has the highest conductivity, followed by a semiconductor. There's a gap in the conduction band and valence band, and then electron has to go from this region to this region first, then it can take place in conduction, then it can move freely. That means it is the conduction in this region is first, this is second in conductivity. Then there is an insulator where the gap between conduction band and valence band is very large, and there is hardly any electron which can jump to this level, so it has least conductivity. So the answer of this question is this particular part. That means the metal is having the greater conductivity than semiconductors and insulators. Okay. Now the question 12. Uh, so question 12 says that 1D potential well, a particle with zero energy has time independent wave function. So let me just first clarify, this wave function has certain, this is actually a e to the power minus x squared divided by L squared, and not the one which is given. Because as per this wave function, you will get any of the answers like here, and not what is given here. This is not a correct wave function representation. That's what I checked, and there was a mistake in this question. So the actual wave function given is something like this, which almost looks like a Gaussian. It's a Gaussian pulse with certain width, which is given by L. Okay, so first of all, then what we need to do is that we can use approximate analysis in order to compute the potential at V of. We need to find the potential at Vx equals to 0. It's an inverse problem. We are given the wave function. We need to compute the potential at x equals to 0. Okay, just a second. So what we are going to do again? We have to use the Schrodinger equation as per the question. And when we use the Schrodinger equation, we can write Schrodinger equation. Let's solve it here. This is question 12. We can use the Schrodinger equation. Again, minus h bar squared by 2m dou square psi over dx square, dou x square plus v of x psi of x equals to e psi of x. What we are given is that it is a particle of mass m with zero energy. Zero energy. That means E is equivalent to zero. Now, I don't know what sort of situation here it is, but we just have to consider the energy of a particle to be zero with given this wave function, and we need to compute the potential. We are going as per the question. Okay, now this thing is zero. That means the right hand side it becomes zero, and we need to compute the v of x. So how are we going to compute v of x is v of x psi of x is equal to minus h bar squared. Oh, minus will go. We are bringing this term on the right hand side. This term on the right hand side, we will get h bar squared by 2m uh, dou square psi over dou x square. Then we can write v of x to be equivalent to h bar squared by 2m 1 over psi of x dou square psi by dou x square. That is it. We need to compute this v of x by computing the second partial derivative of given wave function with respect to x, and we will be getting v of x. Then we can put x equals to 0. Let's do that thing here. Okay, let's compute dou psi by dou x first. What is psi? Psi is a e to the power minus x square over L square. So dou psi by dou x will be a e to the power minus x square by L square into minus 2x divided by L square. Simple differentiation of this. And this is equivalent to a 2a minus 2ax divided by L square e to the power minus x square by L square. Now differentiating it again, we get dou square psi by dou x square. You have to differentiate this thing. Let's take minus twice a over L square out and differentiate the inner thing, this one, because the coefficient is independent of x. So you will differentiate first, differentiating the e to the power minus x square term, keeping x as such, e to the power minus x square L square into minus 2x divided by L square plus, now differentiating x with respect to x, we will get 1 and we will get this term back e to the power this. This is just d by dx of u dot v, which is u dv by dx plus v du by dx, just the product rule. Okay, so now what we are left with is we have to compute dou square psi by dou x square at x equals to 0. When you put x equals to 0, this term will go totally, this term will remain, and e to the power 0 is 1. That means you get this thing, as minus 2a over L square. This is the term on the which you have to use here. Okay, now solving this particular thing here, you get v of x is h bar square over twice m 1 over psi of x. You get minus 2a over L square. Now you have to compute v at x equals to 0. You put x equals to 0 here, you get h bar square by 2m minus 2a by L square. You know that this psi of x is given, and the psi of x is this thing. When you put x equals to 0 here, you get only a. All right. So you will get here 1 over a. Done. All right. So e to the power 0 is 1. You get this a. Okay. So 2 and 2 goes. A and a goes. You are left with h bar square minus h bar square divided by m L square, which is v of 0. And this is the answer of this particular question. Again, there's a mistake over here. The actual answer is minus h bar square divided by m L square, not minus 3. I cannot comprehend how this minus 3 comes up in this question. But maybe if you have any doubt, then you can ask in the discussion forums, or if any one of you will get this minus 3 in this particular question. So this is the answer of this question, and simplistic way of solving the inverse problem of obtaining the potential given the wave function. But we have changed, note that there is a change of the wave function here. One of the reasons why this wave function won't work is because when you will write the potential as h bar square by 2m 1 by psi of x dou square psi by dou x square, because the given wave function has x e to the power minus x square type dependence. And when you put x equals to 0, you get 1 by 0, which is infinite. The way the potential blows up. That means v of x tends to infinity. It blows up. So that's why I cannot, I should say, justify or comprehend how the wave function will be defined like this. Okay, you can come up with your explanations. All right, we have 10 minutes left for this session. Let's move on to the other question, question number 13, which was asked in Physics Gate to 2012. And what this particular thing says, what this particular question is saying is that there's a wave function of a particle moving in a free space. First of all, it's a free space. That means the U or potential term is zero. The electron is not under any potential. It's free. It's free to move. It's a plane wave as per the Schrodinger equation, given as e to the power minus I k x if this is x direction, some coefficient a. Now, they have given the wave function like this. And you know that it doesn't matter what this is a plane wave solution basically, and you know that the energy of the plane wave is given by h bar square k square divided by 2m, energy of a free particle, free electron. It's a free particle energy. It's a particle in 1D. It's a particle in a one dimension. It's not a particle in a one-dimensional box, not at all. It's a particle which is moving freely in vacuum. Okay, so it's having energy of h bar square k square over twice m. Again, how you arrive this, you solve Schrodinger equation like this: dou square over dou psi square, dou square psi over dou x square plus twice m over h bar square. E psi of x is equivalent to 0. You call this thing as k, and k square equals twice me divided by h bar square. And it gives you the energy E equals to h bar square k square divided by twice m, where this k is again the wave vector. This is n pi over, it can be written as L, n pi over x here. X is the coordinate. We sometimes call this as wave. This is the wave vector, and you can call it, it's the inverse of the wavelength. So basically, there are two things I'll tell you. When you have time domain and you have frequency domain, you convert this by using Fourier transform. If you have a spatial domain, you convert this into a wave number by something called as spatial Fourier transform. Spatial Fourier transform. And this thing is basically equivalent to 2 pi over x, just similar thing that f is equivalent to 1 over t. Okay, if you convert t into omega, you write omega as 2 pi over t. Similarly, if you have x space, you can convert it into wave uh, uh, k space. This is called as k space. You write it as 2 pi over x. These are two different Fourier transforms, but similar concept. This is time to frequency Fourier transform. This is space to k space Fourier transform. Okay, it's a spatial Fourier transform. Okay, so the answer of this question is that its energy is the same h bar square k square by 2m. This is the free particle energy. Free particle energy. Free particle energy. Now the cutoff wavelength, the question 14 says that it was asked in EC Electronics and Communication Gate 2014. It says that the cutoff wavelength of light that can be used for intrinsic excitation of a semiconductor with band gap 1.1 electron volt. So there's a 1.1 electron volt band gap of a semiconductor. This is conduction band, this is valence band, and you are hitting it with, let's say, with a photon of energy. This is a photon of energy h nu, and of wavelength lambda, let's say frequency nu. You're hitting the electron, it has to go from this to this particular region. Then at least the energy of the photon should be at least equivalent to the difference, the energy gap. Then only it can go into the conduction band. If it's less than that, it's not possible for the electron to go. It will just go here, or it won't even excite, or it won't accept that photon. That is how fundamentally things work. Now, what you need to find is the cutoff wavelength. You can find energy first for the photon to be equivalent to, which is equivalent to Eg. That should be equal to 1.1 electron volt. Now you know that E is equivalent to hc over lambda. You can compute lambda as hc over E. You can compute this by using the value of HC. You can use the value of HC as 12400 divided by this E in electron volts. And when you use this particular values, this will give you the wavelength in micrometers, and you compute this thing, you will get the answer as 1.125 as the cutoff wavelength of the light. It is the, you see that if you convert this wavelength into frequency, you will have to convert it like this. You can write frequency as c over lambda. That means the photon should have the frequency at least equivalent to EC minus EV divided by H bar divided by H. Only then, or I should write here, let's write it as EG divided by H. This should be the frequency of the photon. Only then it will be accepted by the system and the electron will excite to the higher energy state. And this is the cutoff frequency of the photon. If you convert this into wavelength, you get the desired answer of this question. That is the similar thing what you can obtain from this. Now we move to the question 15. The band gap of the arranged in ascending order germanium and silicon indicates germanium silicon respectively. So we have to arrange the band gaps in the ascending order. Ascending order means smallest first and move to the largest band gap. We know that diamond is an insulator. It has a very huge band gap of approximately, let's say, 3 electron volts. Germanium has a band gap of 0.7 electron volts. Silicon has a band gap of 1.1 electron volts. I have drawn it to scale approximately. And so the order of this, the order for this is that smallest band gap is for germanium, followed by silicon, followed by diamond. So the correct answer of this question is this. Okay, that's why this acts mostly as an insulator. These two are kind of semiconductors. Okay. Now the band gap of a material is 9 electron volts at room temperature. And you know the 9 electron volts is much greater than the KT, which is basically 25.6 milli electron volt. And if you have some energy which is much greater than the KT, where let's say the electron is not able to go from this level to conduction band, then this particular system is going to act like an insulator. So this is going to be act like an insulator. 9 electron volt is pretty huge. You have a silicon which is having a band gap of 1.1 electron volt, but you have something which is with a band gap of 9 electron volts. Then even what happens is that you need at least 9 electron volt for the electron to cross this particular barrier, while it's easy for the electron to go from this particular region to this particular region. Okay, some of the electrons can go from this particular region to this particular region because certain electrons are highly energetic. There is basically, if you know about the density of the states and the Fermi function, you can plot the number of electrons like this. If you consider the 3D, if you consider the density of states in 3D, which are the allowed energy states for electron, and f of E gives the probability of occupying those energy states. When you plot density of states in 3D, it varies as square root of E, and you can show it like this. This is the energy axis. And when you plot the Fermi function, it is basically something like this at a room temperature. And you get a region like this, where there are electrons mostly occupying this particular energy level, but there are certain electrons which are highly energetic. This is something called as Fermi tail, where high energy electrons reside. Okay, so this is the overall picture of how the electrons form a distribution of energies in a certain material. So there are certain electrons which mostly occupy these states, but there are few electrons which can actually have this particular energy present here. in the Fermi tails, and they can actually excite to the higher energy levels. And that's it. That's it for the for this session. We are almost done, and it's almost 8 p.m. But I'm not sure what happened today. Maybe you guys might not be able to find the link. And actually, I have come to know that the assignment problems which you are solving are for 2024, but maybe we have to solve it for 2023 or 2022, which have the similar set of assignment problems. It doesn't matter whatever you solve; these have the similar set of problems, and you can apply the similar concepts there, and to solve it. But I'll make sure that I just uh, I don't get I don't confuse you people with what assignment problems you need to solve, and I will just clarify it from my seniors that what is the issue with these assignment problems. Maybe some of the TAs are solving other set of assignment problems, and I'm solving some other set of assignment problems. But more or less, it doesn't matter because the concepts are similar, and the concepts of the tunneling and the concepts of the potential wells are similar in both of these problem sets. So that's all for it. We will be meeting again next week, next Saturday. Till then, just take care. And if you have any questions, you can anytime mail me uh, on this mail 214076008 @iitb.ac.in. And if you have any mail, you can make any queries. If you have, you can just contact on this email, and I'll make sure I'll reply in maybe one day time period. I'll make sure that I'll do that. Any query you have. And that's it for today. Thank you for listening, or thank you for, if you have understood anything, then you can also visit my YouTube channel, which is Shazan But. I think Shazan, but you can search. There you can find all of these videos. Okay, and that's it for today. Thank you.